What can we do if we have excess phosphorus in the environment? So, first thing, the signs. Excess phosphorus tends to lead to observations of iron and or zinc deficiency, sometimes copper deficiency, um, because of the formation of iron phosphates or zinc phosphates or copper phosphates. And so in terms of toxicity, this is what we see. We see deficiency symptoms. And although toxicity is uncommon in soils grown with the major crops that we grow, it certainly can be an issue in hydroponic systems if you're not careful with phosphorus application rate into the liquid phase under hydroponics. But this can happen in the natural environment. And so think about, what can we do to reduce excess phosphorus? So the reduction of excess phosphorus really depends on what you've learned in this class, right? And this is excess phosphorus in soils. So it really depends on soil pH, right? So if you know the soil pH, you could add a calcium source. If you don't have a readily available calcium source in a system, like under high pH where you have lots of calcium carbonate and you have excess phosphorus and you want to reduce excess phosphorus, you could add excess calcium. You could, under relatively low pH values, if you have excess phosphorus and you don't have enough iron or aluminum for places where phosphorus can be loved in the soil, you could add an iron or aluminum source to help further precipitate phosphorus in those soils and reduce phosphorus availability. The other thing you could do if there are places for phosphorus to be loved in the soil, and when you have excess phosphorus in the environment, is to wait. Because you learned in this class that phosphorus loves to be loved by iron, aluminum, and calcium mineral phases. And so if you give the soil time to react, the phosphorus will react with those phases as long as they are present and available. So I want to share with you this story of waiting. And I'm not going to read all the text on this slide. I'm going to tell you the story because this is a piece of work that myself and others worked on years ago. And this was a biosolids land application program where we applied biosolids at either an agronomic rate or at excess to wheat. And we knew that the excessive application, which was about 7 times the needs of the plant, that was excessive. And we stopped the excessive application rate of, it says 40 megagrams per hectare. It's 18 dry tons per acre added every other year to, this was under dry land conditions. So this is out in the Western United States. And so what you're looking at in these two panels are two different sites. They're side by side. And at time 0 through time 1, 2, and 3, these are years, or I'm sorry, these are croppings after termination of biosolids application at the 40 megagram per hectare application rate in the circles, as compared to a control or background where nothing was added, no biosolids or any fertilizers was added for that matter. And what you see on the y-axis at both of these sites is, this is basically plant available phosphorus concentrations. And the croppings after termination are not quite years. So in these systems where water is limited, you grow a crop 1 year and then you let the soil sit fallow to build up soil moisture for the subsequent crop. So it's every other year. So what we find in both of these sites is that the excessive application rate takes 3 cropping cycles for the concentrations of phosphorus in the soil that the plant would, quote, see to come back to what is the background. That occurred at site A, and it took 3 cropping cycles at site B for the excessive application to come down to background. So 3 cropping cycles is 6 years, and you could do some predictive analysis to determine or fill in the gaps from something that's excessive to something that would be in between excessive and the control. And so this is a story of waiting and letting phosphorus love to be loved in the system by iron, aluminum, and calcium phosphates.